Welcome back. So, now we will see the rotating magnetic field demo. You can see sorry please delete this part. So, now we will see the rotating magnetic. I can see here there is a induction motor here connected to the plug. So, when you give a supply, it starts rotating. So, let me now take out the flange, that means the outer covering, to show you in animated way. So, see, I am taking out the bolts. So, once I take out the bolts, you can see inside there is a winding. So, you see how the north pole, south pole, it is a 4-pole machine. As you can see here, this is a 4-pole machine. This is a 4-pole machine, as you can see. So, there are 4 windings, you see, 4-pole machine. So, this is north pole, this is north pole, this is south pole, this is south and this is south. Flux is entering here, as you can see, flux is entering here and flux is leaving here. So, there are 2 poles, north and north, south and south, north, north, south, south. So, this is a 4-pole machine. So, winding is such that if you give 3-phase current to this is a 3-phase current which is in 3-phase, it is inside the plug 3-phase current. So, these flux patterns start rotating and they are constant, as you can see they are constants, they are constant and they start rotating, you can see. So, you can see once again. So, it is rotating constantly, okay, with constant current. So, now you can see if you just do it in a animated fashion, you can see this is one coil which is having south and north pole, you see. So, this is one coil, okay. So, if you have another coil, let us see one more coil, you can see there are 3 coils. So, that was just one coil, this is one coil, it is a pulsating magnetic field, this is just one coil, one south pole, north pole, it keeps on changing, as you can see, this one coil. So, it keeps on changing, you see sometimes it becomes north, sometimes it becomes south, sometimes north, sometimes south, because of this sinusoidal current variation, just one winding. So, if you have 3-phase winding, what will happen? You can see there is a 3-phase winding in next. So, here there is 3-phase winding, 3 different windings. So, the current is 3-phase. So, what will happen? Let us see. So, you see the flux patterns, they add up and eventually the north and south pole they rotate, they do not pulsate, you can see. So, this is 3-phase winding, you can see this north and south pole they rotate, you can see this north and south pole they are rotating, they are not pulsating. That is the whole idea of a 3-phase distributed winding. So, this rotation cuts the flux of the rotor and the rotor starts inducing EMF and there is rotation, all right. You can see this. There are 2 pole pairs, that was single pole pair, it is a 4-pole winding. So, you can see this also happens, this north and south pole all of them start rotating, you can see here north, north, south, south, this is 4 pole, the other one is, the earlier one is 3 pole. So, you can see this is the concept of whole thing. So, what happens when there is a 4-pole winding? So, what will happen to the rotational speed? Because there are 4 poles, the electrically you are actually moving 360 plus 360, 360, because by the time the current rises up, falls down and comes back, you have already gone 360, but the mechanical speed is, mechanical angle becomes double, mechanical angle where electrical is going half, while electrical is going 360, because north pole to north pole is 360, north pole to north pole again back to north pole is 360 plus north south 180, south north 180. So, like that 4 poles means the electrical degree is 720. In one mechanical rotation the electrical frequency goes double. So, that is why the electrical speed the mechanical speed is equal to the electrical speed by number of pole pairs, that is what is written in the last, right. So, this is the stator winding, as you can see the stator, you can see it was brought out, you can see this is the stator winding, this is laminated, they are put together. So, there are slots, that is a stator winding. So, you can this is how the rotation happens. So, thank you. So, we have done the rotation so we will now get into the next. So, the rotating magnetic field you understood that it is essentially the superimposition of MMF waves due to 3-phase winding. So, that creates a resultant ammeter. So, now what is the physical interpretation? This is a magnetic field vector, either north pole, south pole, they rotate smoothly in the air gap. So, there is no pulsation, it is north and south pole smoothly rotating. Okay. So, that behaves like a magnetic rotor, even though stator where the armature winding is there is not getting rotated. So, that creates a sensation of the rotation. So, that is how these flux waves they cut the conductors on the rotor, they cut the conductors. Sometimes the armature may be static, the rotor may move around it, or sometimes the armature is on the stator, the rotor will move inside it. Induction motors, the rotor is nothing but a set of windings. So, whenever the magnetic flux cuts these rotors in a smooth manner, there is a smooth MMF which is created. Again, some smooth current which is created. Again, if you have a distributed winding in the rotor also creates a sinusoidally rotating field because of the current. So, this magnet which is in the stator and this magnet which is created by induction, in case of induction machine, they interact, these magnets interact, and finally, the rotation takes place. Okay. So, direction of rotation ABC one direction, if you interchange the phase sequence BC, it will become ACB. So, if you want to change the phase sequence, you change like this, you make it ABC or ACB. So, they will opposite. So, swapping two lines reverses the direction. So, now our next is we will go to, so this is the basis of induction machines. So, now we will discuss the polyphase, essentially 3-phase induction machines. 3-phase induction machines, you have seen the pictures, they are the workhorse of industry, we can say workhorse. Workhorse means they need least maintenance, or they are cheaper and they are very robust. That means it will last for longer time, because the rotor is not connected in here. So, the very popular type of motors are known as squirrel cage induction motor. So, we will study the behavior and performance of these 3-phase induction motors. So, it has strong similarity to transformers, because it is by the principle of induction. The stator magnetic field interacts with the rotor. So, you call it induced current in the rotor, and this induced voltage which leads to induced current in the rotor, they interact with the stator flux wave, and finally, the torque is produced. And this is widely used in mining industry. Induction motors will be everywhere, starting from drag line, everywhere, and the dusty environment, they are the most robust things. So, the principle of operation I have told, 3-phase balance supply to the stator, rotor currents are produced by electromagnetic induction, and finally, there is rotation. So, these are some of the pictures of induction motors. So, this is one of the pictures, they are copyright, these pictures have no copyright, that is why I have put it here. So, this is one picture, the motor, you can see there are fins, you can see here. So, let me just tell you. So, these are fins. So, they are required for cooling, so increasing the surface area. So, these fins are responsible for increasing the surface area for cooling. For good cooling. Cooling why? Because there are heats generated because of I square R loss in the stator, then iron loss like eddy current and hysteresis. So, these are losses, and there will be losses because of windage, bearing, etc. All these losses are conducted, and this conduction goes to the here. So, these radiates, if you increase the surface area, the radiation will be more and there will be cooling. Sometimes there are external fans which are connected for cooling. So, this is totally enclosed, the supply is given, this is the terminal box where the power terminal box where the power supply is fed into this, and you can change the phase sequence if you need. So, this is fed here. The terminals of the stator winding is brought out here. So, the stator winding is connected to the supply here. Stator winding terminals are connected to the supply here, power supply, 3-phase power supply. So, there are different stators you can see. You see there are 6 outers, which means each phase A, B, A, B, A, these are 3 phase, these are all 3 different windings, 3 different windings. Each winding will have 2 terminals, A terminal and A dash terminal. Similarly, B terminal, B dash terminal, C terminal, C dash terminal. So, they are connected, they can be sorry, they can be connected in star. So, this is one winding, A dash, B dash and C dash. So, there is dot connection. So, these are the dot connection. You can connect them in star together or you can connect them in delta. So, you can connect them in delta. So, there can be delta and star connection. Sometimes you do delta and star connection both by star delta starting. So, these are the winding terminals which are coming out, different size of the motors. And this is the rotor. This rotor is called squirrel cage. You call it squirrel cage. There are 2 types of induction motors. One is squirrel cage, another is called wound rotor. That means rotor also has an winding like the stator. So, both are there. So, this is very less used. So, the utility of this is less than 2% or 1%. So, this is 98%. So, 98% cases squirrel cage induction motors. So, this squirrel cage means what happens? These are conducting bars, aluminum alloys. These aluminum alloys are fused together. So, that means it looks like a cage. So, if you see there are one ring here and there is another ring here. So, the bars are connected like this. So, this looks like a cage. So, that means 2 different windings and it is a short circuited rotor, as if it is a short circuited rotor, as if it is a short circuited rotor. So, both sides. So, these are some overhang conductors and there is bearing etc. So, this is put inside this. So, this is the rotor. This is called a squirrel cage rotor. So, it is a short circuited rotor with aluminum. It is very robust because it is very strong mechanically. There is no connection here. It is just hanging in the bearings. So, if you look at this, so what happens? The rotating magnetic field rotates at synchronous speed, which is equal to the synchronous speed means what? The speed of the rotor. This is called synchronous speed, rotor speed, which is actual the electrical synchronous speed divided by number of pole pairs. So, that means this omega s is omega electrical by number of pole pairs. So, this is omega s mechanical. So, that means the radian per second mechanical, radian per second electrical. Okay. So, this is synchronous electrical field second. So, this is synchronous speed. So, this because we said that if you go 360 degree in mechanical, electrical will go as many pole pairs. If it is one pole pair, it will go just once. So, electrical mechanical degrees are same, electrical and mechanical speeds are same. But if it is 4 poles, then it will go just double. So, electrical will go double, therefore, electrical speed is more than the mechanical speed. So, if your supply frequency is 50 Hz, that is called the synchronous speed. You can see here I have told you already. So, this is the supply frequency and this rotate, this omega is the supply frequency, supply electrical frequency. This is the speed at which this MMF travels, this is travelling wave, this is the supply frequency. So, this is radian per second, so it is equivalent to EF is 50 Hz, so 50 cycles per second. So, 50 cycles which is 3000 revolutions per minute, this is supply frequency, but the mechanical synchronous frequency may be half or may be same depending upon the number of pole pairs. So, this is what. So, rotating field is essential. So, when the rotating field starts in, what happens? It cots. You can imagine this cots this flux, because this is stationary. Initially imagine the motor is starting. So, during starting what happens? The flux is, that means flux is rotating, rotor is stationary. Rotor is stationary. And flux is rotating. Flux is rotating at synchronous speed. All right. So, when the flux is rotating, so rotor will cut the flux. So, there will be voltage induced and it is shorted. So, voltage will be induced at different magnitude, different phases, because they are all distributed around it. So, there will be current will be circulating. So, Lenz's law. So, a thumb rule is the very cause will be opposed. That means the result will oppose the cause. That means it will create a current pattern in such a way, it will try to oppose the very magnetic field which is rotating. That means when the north pole south pole, as it is rotating, this will also create a north pole south pole. If you make the rotor hold, that means the north pole south pole created by the stator and the current induced will create another north pole south pole, they will lock each other and they will be locked. And if you just leave the rotor, so the north pole south pole created by the rotor will try to follow the stator. That means north pole will attract south pole and south pole will attract the north pole. So, stator north pole will attract the stator rotor south pole. Number one is you are having current in the rotor. So, this current will create again a revolving magnetic field. So, north pole south pole. So, stator north pole will attract the rotor south pole and again stator south pole will attract the north pole. So, the rotor will try to follow, that means it will rotate. So, this is one principle. Other principle is, since the current is flowing here, because of the current CFM, right hand rule, left hand or right hand rule, CFM, the current field motion. So, that means there is a current, there is a field, there will be a force, and there will be opposite force, because north pole exactly after 180 degree there will be south pole. So, they will be opposite and they will create torque couple, they will be same force in same direction, because current reversed. So, what will happen? So, there will be a torque. So, this torque will create the rotation. So, therefore, the rotation will start. Once the rotation will start, NR, the rotor speed will increase, and there is stator synchronous speed ns. So, rotor speed and stator speed difference is known as slip. So, what will happen eventually? The rotor will try to catch up very close to synchronous speed, because so that is where the slip becomes very small. So, if you, so this ns minus nr by ns into 100 is known as percentage of slip. At the starting, nr is equal to 0, the slip is equal to 100% or slip is equal to 1. So, at the synchronous speed, that means the rotor reaches the synchronous speed, slip is 0. So, slip at starting is 1, slip at full speed is almost 0. So, this is how slip changes, and this omega nr increases and slip decreases. So, that is what is the principle of this. So, there are two types of induction motors, what is called wound rotor induction motor and squirrel cage induction motor, as you can see. So, now moving on. So, you can see here, this is the cage rotor I have shown, this is wound rotor, that means there is a rotor winding. So, how the winding is supplied? Through slip rings. You can take out the winding terminals to slip rings. Slip rings means they are connected to the winding and they rotate, and there is a brass. You can see these are brass. So, by means of this brass, you can short circuit these windings, or you can also connect resistances. That way, you can also control the rotor parameters. If you control the rotor parameters, you can change the torque, you can do some speed control, etc. But this is very rarely used, because it is maintenance, because there is a brass which is constantly getting wear and tear. If there is dust, etc., brass will be short circuited. Sometimes the brass is too much wear and tear, there will be sparking. So, this is not generally used, very rarely used, but mostly used is squirrel cage, as I have discussed. The rotor is shorted and it looks like a cage. So, slip I have already told. So, this is the slip formula, S is equal to ns minus n by ns, and the rotor speed, if you know the slip, the rotor slip is very small, n will be close to ns if slip is large. During starting that is a slip is equal to 1, n is 0, and during very low close to the synchronous speed slip is almost small, and this. So, this is how. And the relative frequency, relative speed between the rotor and stator is ns minus n, which is equal to slip times ns. That means, this is called the relative speed between stator and rotor. Stator magnetic field and rotor conductors. So, this is the relative speed between the stator magnetic field and rotor conductors. So, as a result what happens? The relative speed is responsible to induce, because the rotor bars are getting cut by a small frequency s into. So, the frequency of induction in the rotor is small sf. So, the stator frequency is frequency of supply, electrical supply, and the rotor current frequency is s into fe. This is rotor current frequency, the two different frequencies. The stator and rotor are having two different frequencies. Therefore, this whole thing is not linear, the frequency is different. So, therefore, the analysis needs some little transformation. How do I analyze? So, how the rotor slip frequency voltage are induced in the rotor conductors. The rotor current interact with the air gap flux, electromagnetic torque is produced due to this interaction. I have told you this several times. This is how what happens. So, what happens if you look at the torque and speed? Suppose I want to plot the torque versus speed. This is the torque on the, and this is the speed of the motor NR. So, during starting the speed is obviously 0. If the speed is 0, what will happen to the MMF? So, MMF is cutting, the relative speed between the stator and rotor is maximum. So, there is maximum. So, there will be current frequency also maximum. So, there will be frequency also. The voltage by current in this rotor circuit you know, see the voltage by current, there will be current in during starting. So, because the voltage magnitude is more, because the relative speed is maximum. So, what will happen? So, there will be current, so there will be some torque. So, there will be starting torque, always there will be starting torque, no starting problem. So, as the frequency of as the speed increases, there is a starting torque of the motor starts rotating. As the rotating, what will happen? The motor frequency, the rotor frequency drops, because the relative field works. If the rotor frequency drops, rotor circuit has inductance. So, rotor inductance also drops, inductive impedance. So, because of drops, the current may be more. So, torque may increase. Why the torque will increase? Because the rotor currents becomes more resistive, because the rotor current is proportional to rotor voltage V rotor by rotor impedance. This is the rotor current. So, whenever there is 0 frequency, this is completely resistive. So, rotor current creates a torque. As the frequency increase, the rotor speed increases, the rotor frequency reduces, relative speed reduces. So, when the relative speed is reducing, the frequency of induction will reduce and this Z might induce. So, this might have more current and therefore, the torque might increase, but after some time it will keep on increasing. It will again, the torque will fall down, because the voltage will also fall down, the relative speed will become very close, very small, the rotor speed will come down to the synchronous speed. So, again the torque will fall down. So, this will be a kind of characteristic I will see more, but this is the torque speed characteristic of induction. It is starting torque, it will achieve a maximum. So, this is called the torque developed by the motor. So, this is what is the torque developed by the motor. So, the torque initially at the starting torque, there is some starting torque, depends upon the resistance and the inductance of the rotor circuit, because rotor has a circuit also. Rotor circuit is the current flows because of the induced voltage. Induced voltage will be maximum at the beginning, but the frequency of the rotor circuit will be higher, therefore, the impedance may be higher. So, voltage may be higher, but impedance may be higher also. Therefore, this ratio will become little lower, but it will create a starting torque. But as the rotor speed increases, so relative frequency will relative speed will be less. So, voltage will reduce and impedance will also reduce. So, the ratio might go up depending upon the R and L of the rotor circuit. So, it will keep on. So, therefore, this ratio might increase. So, after some time this voltage becomes very small, impedance becomes very small, which is limited to the resistance only. In that case, again the torque will fall, and when the rotor reaches almost the synchronous speed, the relative speed will be 0, therefore, torque will be 0. So, this is the whole magic of induction motor. You do not need a starter most of the time, it will start online. That means, you can have direct online starting. For synchronous motors, you have I have given some hints, the starting torque is not there, you have to make arrangements, but in case of induction motor, starting current is there, starting torque, but sometimes to limit the starting current we do some techniques by this, they are called star delta starting, some kind of starting. So, you can see here torque increases approximately linearly with slip. So, this increases linearly, after some time there is a breakdown torque, again it comes down. Okay. So, this is how the torque speed characteristic looks like. So, we will see. So, normal operating condition slip is about 2 to 10% in general induction motors, which is very close to, that means synchronous speed. If there is a 50 hertz supply, and there are number of poles P is equal to 2, then the synchronous speed is 3000 rpm electrical, which is same as 3000 rpm mechanical. If the number of poles are 4, so this becomes 1500 rpm is the synchronous speed, and electrical speed will be 3000 rpm. So, this is electrical. So, here this is the maximum speed achievable, and if a slip is 2 to 10% slip means the rpm will be 1350, 2% means, so 2% slip is 1470 rpm, that is the rpm, full load rpm. So, that is the rpm at which full load rpm. This is synchronous speed. So, rotor frequency is very low, relative speed is very low. In this case, the relative speed is only 30, minus. In case of Hertz, it will become 50 into S, 2%. So, 2% of 50 is equal to 1 Hertz. So, the slip is very small, 1 Hertz. This is the induced frequency. So, 1 Hertz means mostly resistive. You can see rotor inductance is almost negligible, it is mostly resistive. Motor near like constant speed machine. So, if it is resistive, it is very stiff, torque speed characteristic. Here in this region, it is stiff like this, almost stiff. So, even if you change the load torque, the speed does not change much. So, this will talk about this. This is electrical torque, in this region the slip is very small, 2% here. So, you can change the load torque. So, load torque will be like this. If you keep on this load torque, you keep on changing the load torque, T minus TL is the accelerating torque. So, if you keep on changing the load torque, there will be not change, this is omega speed, the speed will not change much. So, that is why it is called constant speed machine. That means, whenever due to torque variation, so there are two things, the motor and there is a load. So, this is a load is mechanical load. In case of drag line, there is a boom, there are a lot of loads. So, this is load, this is motor. So, this gives a electrical torque and this opposes with load torque. So, T minus TL has to be equal to 0, so that there is no speed change. So, this happens. So, these are called operating points. So, T minus TL, if it is greater than 0, accelerating, if T minus TL is less than 0, decelerating. So, when it decelerates, the electrical torque increases. So, particularly this becomes a constant speed machine, that is why it is called constant speed machine. So, however, induction motor, how do we change the speed? Speed can be changed by changing the supply frequency, by changing the voltage also. So, these are known as variable voltage, variable frequency control, VVVF control. So, this we can do easily speed control of squirrel cage induction motors, and they are used in variable frequency drives, VFD. or adjustable speed drives, ASD. Adjustable speed drives or variable frequency drives. These are the common names. Variable frequency drives. So, these are known as adjustable speed drives. Induction motors. So, you see this is the torque speed characteristic of induction motors. So, this is the starting torque, this is the 100% zero torque. So, now you must be asking some questions, what happens if the phase sequence is reversed. So, this will go in this way, it will go in this way. How about the rotor speed exceeds the synchronous speed? This will go in this way. So, this particular region 0 to 100 is known as motoring operation. So, this is the starting torque. If there is a load torque, suppose you have, so there is a load. So, if you draw the load torque line which is constant load torque, the operating condition will be here, and if the load increases the torque, what will happen? The speed will fall down and the electromagnetic torque. So, this is for constant torque, this becomes a stable operating region, because if the load increases, speed decrease and torque increase. So, again it comes back, stable operating region. For constant load torques. All right. So, this is the torque speed characteristic, and slip is 1 here, slip is 0 here. What happens? Slip becomes negative, that means it goes beyond that. So, these are known as generating, that means it will start generating. So, this is called generating action, this side is braking. So, we will talk about it later on. So, now we have to try to develop the analysis framework for the induction motor. Just like transformer, you know, we had developed equivalent circuit models, single phase, 3-phase transformers, we had developed equivalent circuit models. For induction motors also, we shall develop what is known as single phase equivalent circuit. To analyze the steady state performance, for only steady state performance analysis. So, if you want to look, so you can easily understand that induction motors can be thought of as transformers. Only thing is, transformers there is no rotating. Here there is a secondary winding on the rotor which rotates. So, if you look at the effect like blind person, you can see that even though the induction is by rotation, but still there is induction. In case of transformer, it is because of the flux pulsation. In this case, it is because of rotating magnetic field cutting, relative motion. So, the effect is same, there is induced EMF in the rotor and induced current in the rotor, and because of that there is a power which is getting transformed from the stator to the rotor, just like transformers. In transformers, power got transported from primary to secondary. How? The primary winding gets energized, so it creates a field in the core, and in the core there is magnetic energy. So, this energy delivers to the secondary and it gets transmitted. So, in the same way, here the stator pumps the energy, magnetic field energy, you can consider co-energy. So, that goes into the air gap. Through the air gap, it passes the induction to the rotor, and rotor also, because of the circuit, it develops I square R loss, also mechanical torque. So, the power goes through air gap, just like the magnetic power, here that is called air gap power. So, stator power minus the stator current and eddy current loss, air gap power. Air gap power minus the rotor loss and rotor eddy current loss, then comes the mechanical power. So, this is the flow. Stator power, power input to the stator, minus stator losses. What are the stator losses? I square R loss, copper and iron loss both. So, that gives you air gap power, power gap, air gap. So, this air gap power goes to the rotor. So, this rotor power, how it is consumed? Rotor power consumed, rotor I square R loss or rotor copper loss, rotor copper loss plus rotor iron loss, then mechanical power output. Again mechanical power output goes to the bearing loss, that is windage, friction, etc. Wind, friction due to wind is windage loss, then plus the shaft power, that means the shaft power. So, this is the power balance equation we will study. So, you know shaft power what is available to you plus the friction and windage loss, that gives you power output from the rotor. Again add the rotor copper loss, rotor iron loss, that gives you the air gap power. Again you add the stator iron loss and stator copper loss, you give the input power. So, this shaft power by the input power is the efficiency. So, this whole thing can be an equivalent transformer. So, how we can do per phase? So, in the per phase modeling, line currents are phase currents, line to neutral voltage is used, other phase obtained by 120 degree phase shift. So, equivalent circuit will be derived. Let us see. So, this is the, let me go to this one, this slide. In this slide you can see this is the stator supply per phase, supply is E1 which is equal to V1 supply, let us say. So, what happens, how much is the, so if S is equal to 1, that means this rotor is, S is equal to 1 means rotor is stationary. If the rotor is stationary, E1 and E2 ratio will be equal to fixed, because it will be equal to the relative speed between stator and rotor and number of turns, etc. So, that will be fixed E1 by E2, but the moment there is slip, the E2 will become slip times, because if with slip is equal to 1, the voltage is E2, at slip equal to S, the voltage will be S into E2. When S becomes very small, E2 becomes very small. S is equal to 1, it is E2. So, E1 by E2 at S is equal to 1 is called turns ratio. You can say this is equivalent to the turns ratio. So, this has a frequency of S. So, S is equal to 1, if the impedance is X2, then with S is equal to S, it is SX2, because S is equal to 1, X2 is equal to omega into rotor leakage reactance. So, omega at S is equal to 1 is equal to omega electrical, but when S is equal to S, Sx2, so it will be S times. So, if you look at this, so in the rotor side you can develop this S, you can write that SE2 by R2 plus JSX2. If you divide S everywhere, so you can say this is as if E2 R by S or R2 by S plus JX2. So, this is a huge difference between this and this. This is the slip frequency analysis. This is the frequency at slip S. This is supply frequency. Only the resistance becomes R2 by S. This is at supply frequency. Same circuit, nothing changed. This is supply frequency analysis or synchronous frequency analysis. So, both cases the current I is remaining same. If the current I is remaining same, the magnitude of current square is responsible for losses and power. So, there will be no change. So, what the beauty here it is, even though the frequency of slip is different, what I did is I converted it back to supply frequency by simple transformation. I divided S in the numerator and denominator and I get a circuit like this. So, what happens, I developed this circuit into this circuit. I separated R2, R2 dash, then R2 into R minus by S. So, total will be R2 by S. So, this addition if you do, it will become R2 by S. So, why I did it? I2 square by into R2 will give you the rotor loss, I2 will not change. So, this will be, and this one is not the loss. So, this can be equal to the mechanical power. So, this represents mechanical power, I2 into I2 square into this. So, this is the whole idea of equivalent circuit. So, now getting into the equivalent circuit from the stator side. From the stator side, forget about the rotor. I have stator resistance, stator, leakage will be there, any magnetic winding there will be leakage, that means any flux which is not going to the rotor is the leakage flux, because the stator winding is like this and rotor is very close to it, very small air gap. So, all the flux are supposed to enter, but all the flux does not enter, some fluxes come back. So, these are leakage fluxes. So, these leakage fluxes are responsible for the leakage reactance. So, whenever you supply a voltage, there will be initially drop by the stator resistance, there will be drop by the stator leakage reactance, then finally you get the voltage induced here, and this voltage is responsible for the flux which is known as air gap flux. So, that is air gap flux and the voltage relationship is taken care by Xm, and this component just like the transformer represents the eddy current loss in the core. So, this is what is the stator. When you have a stator and there is a current flowing out, so this gives you stator I square R loss, this gives you stator iron loss. You can also represent part of the rotor iron loss here without difficulty, and this is the voltage which is as if get transformed to the stator side. It is the rotor voltage referred to the stator. So, you can say this is rotor voltage referred to the stator. So, you can see this. So, this circuit is now E2 dash. So, this E2 dash goes to the stator or E2 cap, whatever E2 cap. So, E2 cap is the voltage on the stator. Then this rotor side, this is the circuit, rotor side. In the stator side, this is the circuit. Now, your equivalent circuit is over. So, you can refer to all these impedance to the stator, just like that turns ratio, just you have to divide this turns ratio. This turns ratio alpha, you just divide or multiply or square, you multiply, just like you did for transformers, you refer everything to the stator. So, here refer and represent this whole thing here. So, stator voltage equation, that means rotating gap flux conduces a counter EMF in the stator. Yes, obviously, because rotating air gap flux also induces voltage into the stator. It induces in the rotor, it also induces in the stator. So, this makes a counter EMF in the stator, and terminal voltage differs due to stator impedance V1 cap is equal to E2, and this represents the stator copper loss, leakage reactance drops, decomposition of stator current. So, you have to decompose in two components, one is the rotor component goes to your, this is power air gap and this is the magnetizing component. Okay. So, these are the things we will discuss from next class. Thank you.